Good afternoon. My name is Marian Verhelst, professor at the KU Leuven in the MICAS research group, and I'll give you an update of our research group within the OmniDrone project in the last year. The MICAS research group has within OmniDrone always focused on enabling high-throughput neural network processing, specifically on high-resolution images. And we do that already since a couple of years through a methodology called depth-first processing. Let me here explain you how depth-first processing works in comparison to the traditional layer-by-layer processing. In layer-by-layer processing, you basically compute neural network layers with a complete layer at a time. This basically means that I'm starting the computation of a next neural network layer as soon as a complete previous layer has been computed. So I compute a whole layer, all the output activations, and only when that is done, I go to compute the next neural network layer. In a depth-first processing, on the other hand, here on the right, you don't do that. You basically compute a certain neural network layer, and as soon as you have enough pixels of that one computed to start computing the next layer, you continue deeper into the network. So I'm no longer computing full layers at a time. No, I take pixels and I propagate them as far as possible to the network, and then I take a next pixel and so on. And it turns out that this is a better approach if you have very large image resolutions and hence very large intermediate feature maps, if they dominate over your network weights. Now, MICAS has been working on this concept since a couple of years. What did we do in 2020? Well, we made both an FPGA mapping of this and optimized it, as well as a custom chip implementation. I'll first start with the first one, the FPGA implementation, where the goal was not to have a hardwired mapping of a single neural network on FPGA. No, we wanted to make a programmable FPGA implementation that can still be programmed to deal with a varying number of layers, varying dimensions of the network layers, varying image sizes, and so on. The goal was to keep it flexible, yet make it very efficient for high-resolution images and use as many FPGA resources as possible to have a very high throughput. We did this by, first of all, optimizing the way that we implemented this depth-first principle, especially on the granularity with which we implemented. Because you can do this depth-first approach on a pixel basis, where one pixel is propagated through the whole network, on a line-based approach, where you compute rows of the image and propagate them through the network, or more coarser granularity with multiple rows at a time. We found the best trade-off between memory usage and speed to be this line-based approach that we then implemented. On the FPGA, we use as many of the DSP resources as possible to implement as many multiply accumulate blocks as we can, and they are then arranged in a two-dimensional array of multiply accumulate units that can share information through broadcasting and pipeline. And the dimensions of this array are organized such that you can still map neural network kernels with varying sizes efficiently on them. So we basically want to be able to program this for a 1x1 filter, a 3x3 filter, a 5x5, a 7x7, and still have very high utilization and usage of my computational framework. I cannot explain all of this in depth, but there is a TCAS 1 paper accepted, a journal paper accepted with all the details that you might be interested into. With this flexible programmable data path, we then complete the rest of the architecture. It is controlled by a set of finite state machines that are programmed by instructions that come from the host. So this is to program different neural networks in there. It has its connection to a memory subsystem that feeds in all the data needed for processing. And again, that's flexible regarding the dimensions of the neural network layers we're dealing with. And that implements this depth-first approach. And then, of course, we have the logic for quantization, activation functions, and so on. This architecture was then assessed across various FPGA implementations of the same family, going from smaller to larger FPGAs. And for each of these FPGA generation, we map both the utilization, the clock cycles, and the throughput that we get with either a layer-first approach and a depth-first approach. And without, again, being able to go into details for all of them, You see here on the bottom that for the different FPGA generations, you get a significant throughput boost because we go with this depth-first approach. And this is especially because the stalling, when you have to wait for new data to come to be processed by the network, reduces significantly because the depth-first approach deals with the data more effectively, efficiently. It has to fetch the data less back and forth from external memory. I let the main designer of this, Steven, give a short explanation and a demo of what he effectively built.
Hello everybody, my name is Steven Kolleman and I'm a PhD student of MICAS KU Leuven and I work in the team of Marian. In this video you can see an experiment which explains my flexible high utilization depth-first FPGA implementation. We would like to process a denoising CNN here. On the top left you can see a noisy image and at the top right you see the denoised image. It is also shown in which order the data are processed on the FPGA, which you can see here at the bottom. Each image is divided in vertical sub-images and the presented hardware architecture performs the computations for each of these sub-images row by row in a depth-first way to minimize the I/O communication. The other two plots at the bottom show the same operation as simulated for other FPGAs. These are bigger, so therefore more computations can happen in parallel. Therefore, each sub-image is wider. Each FPGA also has a different clock frequency and that's also taken into account here to compute the actual throughput. I would like to thank you for your attention.
Again, this table finally summarizes the achievements we got compared to other works in the state of the art. What I want to highlight is that we're much more flexible towards what kind of neural network layers we support and that we can map many different types of high image resolution workloads like super resolution, segmentation, denoising, and so on because of this built-in flexibility. Moving on swiftly to the next topic is that we made a custom chip that can again do programmable depth-first execution. So it's an instruction programmable chip, but now really pushing towards very high throughput by trying to put as many multiply accumulates as possible on a very advanced CMOS technology. Again, we try to extend the flexibility further by supporting now not only anymore the traditional neural network layers, kind of convolutional traditional layers, but now also things like pointwise and depthwise layers, shift nets, and so on, which are harder to map. Again, of course, the core of this implementation is a big array of multiply accumulate units. In this case, we have 2,000 different multiply accumulate units that are organized, first of all, in 128 columns that deal with 128 different input pixels. And each of them gets a different weight from a different output channel in the vertical direction. So every input pixel is multiplied with a weight for another output channel, and every weight for an output channel is multiplied in parallel with different input pixels. This allows you to have good parallelization, yet with a reduced amount of input data fetches from memory. You see on top some shifters and some flexible control here. This is to, again, minimize the amount of memory accesses while dealing with the different multiplications or data fetches normally needed for different kernel sizes. Beyond broadcasting inputs across MAC units to be reused, the output of such a MAC unit is in a pipelined or systolic fashion propagated back up into the feature memory, where every time it goes to the next MAC unit, data can be pushed up efficiently to go all the way into the feature memory without long wires that have to be going from every single MAC unit into the feature memory. So you only need a single connection backup. It's important here to mention that there is double buffering in these registers such that it can basically start a calculation already in the MAC unit while results are being clocked out. And in this way, we never have to wait and lose throughput because we are clocking out results. A special feature in this data path is also that you can efficiently map depthwise, pointwise layers. And to do that efficiently, especially the depthwise part needs attention because it's typically very hard to get high utilization in a depthwise filter. What happens in this case is that the MAC unit or the MAC array splits into two. An upper part where the first, for example, 3 lines are dealing with a depthwise convolution by doing a 3x3 filter basically on 3 parallel rows. And then across 3 clock cycles. And then the bottom, for example, 13 layers will in parallel be doing a pointwise layer on a pipeline version of these depthwise outputs. So this basically keeps a complete MAC array useful or busy, utilized, where the top part is dealing with the depthwise convolutions, and in parallel, again in a depth-first fashion, the bottom part is dealing with the pointwise implementation or execution. And this allows us to get very, very high throughput and very good utilization even for these difficult pointwise, depthwise implementations or mappings. Finally, there's many power optimization tricks in this hardware. For example, that we're not doing a multiply accumulate for every possible A and B that come in. No, if the system detects that either A or B is 0, it first of all gates these inputs A and B so they don't cause toggling in the multiplier. Moreover, it also gates the update of this partial sum, and it even gates the update of the address into the register file to maximally save power in function of sparsity. So in this table, you can see that in function of the weight sparsity here vertically and the data sparsity horizontally, this allows you to save up to 40, 60, even 85% if you have super high sparsity of power consumption. These are relative power consumption numbers. So this saves a lot in typical, let's say 50-50 or 60-60% sparsity numbers. It saves more than a factor of 2 in energy consumption of this chip. Finally, this is the chip as it's taped out. This is a picture taken from under the microscope because we have the chip back in the lab. It's 7mm square in a 12 nanometer GF technology. It holds 2000 multipliers and about 1.5 megabyte of on-chip memory. We want to push it in the lab to run up to 1 gigahertz in speed, which would give it a 4 tera operations per second throughput, and this hopefully at about 1 to 2 watts of power consumption. This chip is currently being put into a whole measurement infrastructure. The chip goes in a packet, the package goes on a socket, and the socket is then connected to an FPGA board to be able to toggle the chip and measure its functional correctness and also its power and throughput efficiency. And I let the designer of this, Koen, tell you about the chip and its measurement setup.
Hello, I'm Koen from MICAS at KU Leuven. In this movie, I'll show you the current measurement setup for the chip. This starts with the chip itself, now in the middle of the frame. It is connected to the package with small bond wires that you can see. This package connects the chip to the PCB beneath. In turn, this PCB connects to 3 things. First, a much larger PCB with an FPGA, which is currently invisible because it's at the bottom of the PCB. Within the FPGA is a built-in CPU. Let's boot that already. Secondly, the chip is connected through the power cables to the lab power supply. We already turned this on as well. Then we can see it's powering the chip's core at 0.8 volts and its I/O at 1.8 volts. Currently, the chip consumes only a small current of 68 milliamps. That is because it is still in reset mode and not receiving any clocks. Third, an oscilloscope is connected to the chip through the PCB. It currently shows 3 signals: the start signal, the chip's internal clock divided by 1024, and a running signal coming from the chip. Meanwhile, the CPU of the FPGA has booted Linux, so let's log into that. If we then run the program, it starts with providing the clocks and releasing the reset. We can already see the current towards the chips increase to 188 milliamps instead of the earlier 68 milliamps. The chip is now ready to start actually doing something. Next, we send the data to the chip so that it is something to do calculations on. Having done that, we can run a convolutional block. In this case, this block is looped in order to prevent it from being done nearly instantaneously. This allows us to see the power consumption while it's running it. So, after starting that, we can see on the power supply that the chip now draws a lot more current, about 937 milliamps. At 0.8 volts, that means the chip is consuming about 750 milliwatts. On the oscilloscope, we can see that the start signal has been given and that this was quickly followed by the running signal, which then remained high. That's because the end of the program is off screen because we programmed it to run for several seconds. That was a current measurement setup of my chip. Thank you for your interest and see you later.
And this also concludes my presentation. Thank you for your interest, and I look forward to talk to you again soon if COVID allows us to get together again. Thank you.